You can manipulate the content of zip files from within a Java program. To demonstrate how to work with zip files, I have put together 3 simple programs. The first one can be used to construct a zip file. This program accepts a list of file names on the command line and uses them to construct a zip file. This class has just one method, the create method. The first parameter is the name of the zip file to be constructed, and the second is the array of file names to go in it. All of the work is done inside a single try block because some of the methods can throw I/O exceptions. First, the zip file is created by opening a file output stream object. Now, these examples are kept as simple as possible so you can see how they work. Normally, you might want to check for the file name being in the right format, that is, whether it has a zip suffix on the end, and you can add one if it doesn't. You might also want to check whether the file already exists. Anyway, this file stream is used to construct a zip output stream object. It is this object that will get the data into the right format to be stored in a zip file. It supports the writing of files in both compressed and uncompressed form. The default is to compress them. Now, this loop executes once for each file to be copied. Each file is read as a file input stream. Now, the complete path name of each file is stored in the zip file, and the file separators inside the zip file are always forward slashes. If you happen to be using some operating system that uses some other separator character, that will need to be changed with a replacement like this. This is a portable way of doing it. A new zip entry object is constructed using the file name because it's to be stored inside the zip file. The entry information itself is written to the file as a new file header. Remember, the names of a file are not actually a part of the file, so it must be written separately. In a loop, the body of the entire file is copied. Finally, the end of the file is marked, making the entry complete. Finally, the input file is closed, and the loop starts over for the next file. This command line will build a zip file containing the 2 named files. That builds the zip file. You can use regular zip utilities to unpack it or to look inside it. I've got a program that will show its contents. This program has the one method named list. It creates a zip file object based on the file we just created. The entries method returns an enumeration containing all the zip entry objects from the file. This program then iterates through the list and prints the name from each entry. It does this for the zip file we just created. Here's what it looks like when you run it. I know it doesn't show up here because there are no subdirectories, but the complete path names of all the files is what's printed. This program extracts the files from a zip file and stores copies of them on the local disk. This class just has the extract method that is constructed about the same as the list method in the previous example, except this one does a bit more inside the loop. The getInputStream method is called for each zip entry, so the body of each of the stored files can be read from the zip file. The name of each file is used to create a local file using fileOutputStream. In this loop, the data is read from the zip file and written to a new file. The file information is uncompressed as it's read. At the bottom of the loop, both the zip file entry and the new output file are closed. After the program has been run, all the files are unpacked and restored to their original conditions. One thing I need to mention, if you want to include directory entries in your zip file, you can. They're just like regular file entries, except for two things. They have no body data like file does, and the name always ends with a slash. Some unzip utilities will use such directory entries to create directories when it unzips the files. In your program, you can call the zip entry method isDirectory and create any non-existent directories. Okay, one more thing. You can read and write the gzip format by doing everything the same as I've shown you here, but use the gzip input stream and gzip output stream objects for the I/O. In the next lesson, we'll take a look at working with another variation of the zip file, the jar file. The previous lesson was about zip files. In earlier lessons, we looked at using the jar tool to construct jar files and use them to deploy Java programs. A jar file is a zip file organized in a special way, and the classes that handle zip files have some direct subclasses that can do the same sort of things with your jar files. The first job is to create a jar file. This program accepts a list of file names on the command line and uses them as content of a jar file. This class only has one method, the create method. The first parameter is the name of the jar file to be constructed, and the second is a string array of the names of the files that will go into the jar. A jar file contains a manifest file, which is a simple text file. I'll show you the contents of it here in a minute. This file stream is used in the construction of a manifest object. Then the jar itself is created by opening a file output stream. The file stream and the manifest are both used as the basis for constructing a jar file, a jar output stream. It is this object that will get the data into the right format for a jar file. This object will also write the manifest file to the jar. Just like with a zip file, the file writing supports both compressed and uncompressed forms of files. The default is to compress. This loop executes one time for each file to be written to the archive. Each file is read as a file input stream. The complete path name of each file is stored in the jar file, and the file separators inside the jar file are always forward slashes. If you're using an operating system that uses some other separation character, that will need to be changed with a replacement like this. This is a portable way of doing it. A new jar entry object is constructed using the file name as it is to be stored inside the jar. The jar entry information is written to the file as a header for the file's data. In a loop, the body of the file is copied. Finally, the end of the file is marked, making the entry complete. The input file is closed, and the loop starts over for the next file. This command line will build a jar file containing one class file, itself. The new jar file contains the class file and the manifest file. Let me show you the manifest. You might think that by its name the manifest file would contain a list of the contents of the jar, but it doesn't. As a minimum, it contains the manifest file version number 1.0 and a brief description of the creator of the jar. You can put anything you like in as the creator. This manifest also includes the main class of the jar file. This program can be used to list the contents of the jar file. It has this one method named list. It creates a new jar file object based on the file that we just created. The entries method returns an enumeration containing all the jar entries from the file. This program simply iterates through the list and prints the name of each entry. Now it does this for the name of the file that we just created. but you can do it for any jar file by changing this name. Here's what it looks like when we run it. One subdirectory is in the jar file, the meta.inf directory, and it contains the manifest file. A more complicated jar file will have other files in the meta.inf directory and possibly other subdirectories with other files. The jar extract program works just like the zip extract program did. In fact, you can use the zip extract program on a jar file. They're exactly in the same format. Or you can use your regular unzip utility on a jar file. However, if you want to write your own extraction program, you may want to add directory handling. The file class has a couple of methods that can be used to construct directories. The mkdir method will construct a directory for you. The mkdirs method can be used to construct an entire path full of directories. Coming up in the next lesson, logging the actions of Java programs so you'll be able to retrace their history. Logging is the act of a running program leaving a record of its actions. Such logs come in handy for software developers. Having the ability to retrace the actions that a program takes can be very helpful in diagnosing problems. It helps at all stages, from constructing the general layout to the final integration testing. When software fails at a remote location, it's very handy to be able to retrace its steps. Without some sort of tracking, a post-mortem is almost impossible. If the logging is made available to the user, some users will be able to trace their steps and analyze their own problems. Now, this is mainly simple logging of common problems. Logging requires overt action by the application. The application makes calls to methods of the logger object to make an entry in the log. The logger creates a log record object containing the log entry and passes that to the handler. The handler reformats the message and sends it on to its final destination. Now, that could be to a display program, an internet connection, a file, another program, or any place that you would like your log entries to go. In fact, it's possible for a single log entry to be passed to more than one handler and wind up in more than one destination. In a more complex system, some handlers may pass on the message to other handlers. You could, for example, have one handler maintain a short-term log in a ring buffer, while another handler makes and keeps a log linear file. Filtering could be done to the logging by the application. This is often done to reduce the amount of information being logged, and that helps system efficiency. Some messages are just discarded. The level of filtering can be adjusted while the program is running. Filtering can also be applied to the individual handlers. That way, different handlers can log different levels of detail. Filtering can be adjusted and handlers can come and go while a program is running, so a logging system could get very sophisticated. You can envision a system running in a remote location and the support for it having the ability to contact a system, crank up a handler, and monitor the actions of the remote system as it runs. The filtering is controlled by the severity level of the log messages. An object of this class can be used to set the logging level of a method. Enabling logging at one level enables the log at all higher levels. The highest level is severe. This level is normally reserved for reporting some serious failure. If a condition occurs that prevents the program from continuing, it should be reported as severe. A warning message is used to report something that could possibly be a problem, but everything's still working okay. These are messages like the file already exists or the file was not found. The program is still running fine. This level is for informational messages. This is commonly used to simply report status. This level is used to report configuration settings. Knowing the configuration can be very important in diagnosis. The lowest three levels, are for tracing information. They can be used to track the flow of logic through the program. Tracing can create a very large log, and it can be handy to trace at different levels of detail. Those are the fundamental ideas behind logging. The next lesson is a concrete example of setting up and using a simple log system. Logging in Java can get as complex as you would like for it to. You can have multiple loggers working simultaneously and logging all at different levels. You can have it so that different parts of your program logs at different levels, and you can send log information to different places. I just want to show you what's involved in setting up a simple logging system. This is about the simplest way to go about setting up a logger. This one line, not inside any method, sets up logging by getting a logger of the specified name. Now this zero-length string is the name of the global logger. You can use any name you'd like in here. The same name will always get the same logger, so different classes using the same name will be using the same logger object. And if you want, you can have different loggers running in the same program, but to do so, you would need a fairly complicated logging scheme. Here, in the constructor, the first entry is made into the log. The name of the method used to make the entry determines its level. This is the info level. Here are fine entries being made to trace the entrance and the exit of the demonstrate method. And a finest entry is made, logging the iteration of each value in this loop. Here's what happens when you run it. The info message is displayed, but it's the only one. You should know that there is a default handler, the console handler. I'll have some more information about that here in a minute. Also, the default is for only messages of the info level and above to be reported. The others are being discarded by the filter. This program is the same thing, except the filtering has been modified to accept messages of the finer levels. A call is made to getHandlers to return an array of all the handlers that this logger is sending messages to. The filtering level of all the handlers is set to finer, which is the setting that will allow all messages except the finest through. Now in this example there is only one handler, the console handler, but this code will work for loggers that have multiple handlers. If you had multiple handlers, you could set different ones to different filtering levels. Of course, the logger itself has a filter setting, so you will need to set it so the messages will get to the handlers. Setting the level this way will affect the logging in all of the classes using this same logger, so you'll only need to do this once. Now we get a different look when we run it. This is the same result we got before, except the two finer level messages are also logged to the screen. This traces the beginning and ending of the demonstrate method. Notice that each log entry is in 2 lines. That's just formatting done by the handler. You can completely change the format and destination of the output by changing the handler. The java.util.logging package has a few handlers, one of which is the file handler. You can add new handlers to the logger by creating the handler and calling the add handler method. This particular handler has to be instantiated inside a try block because it opens a file for output and could possibly throw an exception. Now this program only includes this handler along with the console handler. And the level of all handlers is set to finest, so all messages will get through both. Now, it's more common to limit the console handler to only severe messages, and you can do that on the command line by running the program this way. This command defines a property that defines the logging configuration file. In this example, the logging configuration file just sets the console handler's level to severe, overriding the setting in the program. As you can see, no messages came to the screen. That's because there were no severe messages logged by the program. However, the handler logged everything. This is the log file. As you can see, it formats the messages in XML, and every message was logged, even those including down to the finest level. This is the configuration file that was used to bump the console handler up to the severe level only. There are a lot more things you can do in the log configuration file. This is the default file name. It was installed when you installed your JRE. It's fairly well commented and full of examples, and it's the one used when you don't specify one on the command line. You can write your own handler to format your logs the way you would like to have them. It's easy to do. Some handlers come with Java, so you can take the one that is most like the one you want to write and use it as your model. Just download the Java source and start with the one you like. You've seen the default console handler, and you've seen the file handler that formats all the messages in XML. You may want to look at the memory handler, which keeps the latest messages in memory, or you may want to look at the socket handler, which writes messages into a socket over the internet. The stream handler is intended as a base class for the development of other handlers. Logging can be very important, so it's important that you do it right. I want to make some comments about logging from my personal experience. For logging to work, you need to consider three things. It needs to be easy for a programmer to insert logging instructions when he is working on the code. If it's complicated, he simply won't do it, or at least he won't do it as often as he should. And make sure everybody knows what the levels are and how to use them. 3 levels are usually enough and easy to keep straight. Whenever a message is sent to the log, it should be flushed to disk before execution continues. If messages are being held in memory and the system crashes, you don't know where it crashed because you lost the latest messages. It should be easy to decipher the logs because you will need to be able to comb through them to find clues. The next lesson is about some classes that you can use to handle regular expressions. Regular expressions have been a part of computing since the first days of Unix. Some programs use a simplified form of regular expressions, and this simplified form is sometimes referred to as wildcards. But wildcards are only a small face of regular expressions. The pattern class can compile a regular expression into a form that can be used to match against strings. The matcher class can do the work of matching a string against a compiled regular expression pattern. You can compile a matching pattern and test for a string match in a single statement like this. This is the pattern to be matched. Letters and numbers match themselves. The period matches any character. This is the string to be matched. The static method matches compiles the pattern string and uses it to try to find a match in the string. If it finds a match, the method returns true. Then the pattern and the match are both displayed. The pattern matches the string. The only problem with this approach is that the pattern has to be compiled every time you use it. This is an example of compiling the pattern ahead of time so you can actually use it over and over. It uses separate pattern and matcher objects. In this example, the \W is used to match any word character, that is, any letter. Now, the backslash has a special meaning in Java when you declare it in a string like this, so you need to put in the backslash twice to get 1. This string is compiled twice, actually, once by Java and again by the pattern compiler. Anyway, the first thing that happens in the program is the pattern is compiled into the internal form and a pattern object is produced containing it. Then the matcher method is used to produce a matcher object that contains both the pattern and the string to be matched. Now, no matching has been done yet, but the matcher is ready. There is a good reason for this delay, and I'll be showing you why here in a minute. The matches method does the comparison and returns true. Here's what happens when it runs. You can see that the string matched the pattern. Pre-compiling the matching pattern this way is the most efficient thing to do if you are going to use the pattern repeatedly. And there are two ways you can reuse a pattern. Here's one of them. This is an example of a pattern that will match any one of a group of strings. If you include a group of characters between square brackets this way, it will match any one of the characters included. This example will match any vowel. In this example, the strings on the command line are all matched against the same precompiled pattern. Here's how you run it. This pattern will match 5 of these 6 strings. For a string to match, the middle character must be one of those between the square brackets in the pattern. By the way, it's a good idea to have a little program like this one to test your regular expressions. You can use pattern matching to scan through a block of text and locate all the matches. This is a very simple pattern. The word bark appears 3 times in this block of text, and the matcher can be used to find them all. You compile the expression as usual and then create a matcher object containing both it and the block of text. The find method starts looking for the pattern at the beginning of the text and returns true if it finds it. The start method is then used to find the index of the starting character of the found string. You can also call end to locate the last character, but that's not used in this example. This example displays the offset into the text of the first character of the found string. Then, starting at the first character following the previous find, the matcher looks for it again and continues as long as it's found. Here's how it runs. This program locates all 3 instances of the matching string inside the block of text. This is probably the more common use of regular expressions. And there are lots of regular expression constructs. Let me show you some of the more common ones. You saw this one where any one of the included characters will be matched, and this is just the opposite. This will match any character except the ones in the brackets. You can use a hyphen to represent a range of characters. This will match any letter, upper or lower case. The qualifier operators are used a lot. Any one match, a single character or one of the matching items, followed by a plus sign, will be matched if it appears at least once, but it may appear many times. Followed by an asterisk, any match can be repeated 0 or more times. Followed by a question mark, the match is optional. It's not required, but it can also appear more than once. This means that the match must appear n number of times. There are lots of other operators you can use in matching patterns, but these are probably the most common ones. You can check for blank spaces, tabs, end of lines, beginning of lines, and just about anything else you can think of. You'll find them all described in the Java API documentation of the pattern class. In the next lesson, we're going to look into the storage and retrieval of user and system preferences and configuration settings. This package makes it possible to store and retrieve preferences, also called configurations. It's stored in such a way that it will persist from one invocation of your program to the next. The preference information can be stored in a variety of file types. It can be anything from a complex database arrangement to a flat file, but that doesn't matter to you. That's all automatic. The information is organized in hierarchical nodes. There are multiple collections of nodes. Each user can have his own collection of preferences. This normally includes things like fonts, colors, and window sizes. All users share the same system values. This is information that can be the same for all users, like where the program files are located. The organization is like that of a file system, so a name may not be unique. You can tell them apart by where they are located in the tree. Also, the items in the tree are addressed by a path name. You can use both absolute and relative path names, just like with a file system. Absolute path names start with a slash character. You don't have to flush output to make sure the data persists. Normal termination of the JVM flushes the data to disk, so you don't have to worry about it. This example returns the node of the user preferences for this particular application. This call to user node for package positions to the node by using the class object of this object. Actually, it's done this way to get the package name. Every application is made up of a group of classes, all of the same package. So the package name will be a unique identifier for the application. This example doesn't have a package name, so it uses the anonymous package, which works fine for development, but it's not something you want to do in production software. If the name you choose is not already defined in the preferences, this method call will define it. Anyway, this example just prints out the name. Here's what happens when it runs. This is how the name of the anonymous package appears. If it had been a regular package name, it would have looked like the path name of a directory with slashes used for separators. This program also accesses the user node for the anonymous package. By the way, the system tree is accessed in exactly the same way. You just replace the word user with the word system. Now this example adds a preference entry. Every preference is in the form of a pair, a key and its value. The key is always a string. The value can be any one of several data types besides an int. It can be a string, long, float, double, boolean, or a byte array. Each type has its own put and get method. There, this program should have added the value 6 for the number of bullets, and the value should persist and be available to any other class of this package. This program should access the same node because it's being run by the same user and it's using the same key to retrieve the value. Notice that the method to retrieve the value has two arguments. The first one is the key, as you'd expect. The second one is the default value. If for any reason the key is not found, this method will return the default value of 8. Whatever value is returned, this method will then print it out. As you can see, the get method returns the value of 6, the value that was stored in the preference by the other program. Remember, every user can have a different value for the same key, and any user who has not defined a value will get the default. The next lesson is about using the timers that are available to you in the swing package.